In this video, I'd like to tell you about learning curves. Learning curves is often a very useful thing to plot if either you want to sanity check that your algorithm is working correctly or if you want to improve the performance of the algorithm. And learning curves is a tool that I actually use very often to try to diagnose if a particular learning algorithm may be suffering from a bias or a variance problem or a bit of both. Here's what a learning curve is. To plot a learning curve, what I usually do is plot JTrain, which is the, say, average squared error on my training set, or JCV, which is the average squared error on my cross-validation set, and I'm going to plot that as a function of m, that is, as a function of the number of training examples I have. And so m is usually a constant, like maybe I just have 100 training examples. But what I'm going to do is artificially reduce my training set size, so that deliberately limit myself to using only say 10 or 20 or 30 or 40 training examples, and plot what the training error is and what the cross-validation error is for these smaller training set sizes. So let's see what these plots might look like. Suppose I have only one training example like that shown in this first example here, and let's say I'm fitting a quadratic function. Well, if I have only one training example, I'm going to be able to fit it perfectly, right? If fit a quadratic function, I'm going to have zero error on my one training example. If I have two training examples, well, with a quadratic function, I can also fit that very well. So even if I'm using regularization, I can probably fit this quite well. And if I'm using no regularization, I'm going to fit this perfectly. And if I have three training examples, again, I can fit a quadratic function perfectly. So if m equals 1, or m equals 2, or m equals 3, my training error on my training set is going to be 0, assuming I'm not using regularization, or it may be slightly larger than 0 if I am using regularization. And by the way, if I have a large training set and I'm artificially restricting the size of my training set in order to plot JTrain, here, if I set m equals 3, say, and I train on only 3 examples, then for this figure, I'm going to measure my training error only on the 3 examples that I actually fit my data to. And so even if I have, say, 100 training examples, but if I want to plot what my training error is for m equals 3, what I'm going to do is measure my training error only on the 3 examples that I've actually fit my hypothesis to, and not on all the other examples that I had deliberately omitted from the training process. So just to summarize, what we've seen is that if the training set size is small, then the training error is going to be small as well, because if you have a small training set, it's going to be very easy to fit your training set very well, maybe even perfectly. Now, say I have m equals 4 examples. Well then, a quadratic function can no longer fit this data set perfectly. And if I have m equals 5, then maybe a quadratic function can fit this data so-so, but as my training set gets larger, it becomes harder and harder to ensure that I can find a quadratic function that passes through all my examples perfectly. So in fact, as the training set size grows, what you find is that my average training error actually increases. And so if you plot this figure, what you find is that the training set error, that is the average error on your hypothesis, grows as m grows. And just to repeat, the intuition is that when m is small, when you have very few training examples, it's pretty easy to fit every single one of your training examples perfectly, and so your error is going to be small. Whereas when m is larger, then it gets somewhat harder to fit all of your training examples perfectly, and so your training set error becomes a little bit larger. Now, how about the cross-validation error? Well, the cross-validation error is my error on this cross-validation set that I haven't seen, and so when I have a very small training set, I'm not going to generalize well. I'm just not going to do well on that. So right, this hypothesis here doesn't look like such a good one. And it's only when I get to a larger training set that I'm starting to get hypotheses that maybe fit the data somewhat better. So your cross-validation error and your test set error will tend to decrease as your training set size increases, because the more data you have, the better you do at generalizing to new examples, or just the more data you have, the better the hypothesis you fit. So if you plot JTrain and JCV, this is the sort of figure you get. Now, let's look at what the learning curves may look like if we have either high bias or high variance problems. Suppose your hypothesis has high bias, and to explain this, I'm going to use our standard example of fitting a straight line to data that can't really be fit well by a straight line. So we end up with a hypothesis that maybe looks like that. Now, let's think what would happen if we were to increase the training set size. So if instead of 5 examples like we've drawn there, imagine that we have a lot more training examples. Well, what happens? If you fit a straight line to this, what you find is that you end up with, pretty much the same straight line. I mean, a straight line just can't fit this data, and getting a ton more data, well, the straight line isn't going to change that much. This is the best possible straight line fit to this data, but the straight line just can't fit this data set that well. So if you plot the cross-validation error, this is what it'll look like. Over here on the left, if you have a really minuscule training set size, like you have maybe just 1 training example, it's not going to do well. But by the time you've reached a certain number of training examples, you've almost fit the best possible straight line, and even if you end up with a much larger training set size with much larger value of m, you're basically getting the same straight line. And so the cross-validation error, let me label that, or test set error will plateau out or flatten out pretty soon once you've reached beyond a certain number of training examples that lets you pretty much fit the best possible straight line. And how about training error? Well, the training error will again be small, and what you find in a high bias case is that the training error will end up close to the cross-validation error. Because you have so few parameters and so much data, at least when m is large, the performance on the training set and on the cross-validation set would be very similar. And so this is what your learning curves will look like for if you have an algorithm that has high bias. And finally, the problem of high bias is reflected in the fact that both the cross-validation error and the training error are high, and so you end up with a relatively high value of both JCV and JTrain. This also implies something very interesting, which is that if a learning algorithm has high bias, as we get more and more training examples, that is, as we move to the right of this figure, we'll notice that the cross-validation error isn't going down much. It's basically flattened out. And so if a learning algorithm is already suffering from high bias, getting more training data by itself will actually not help that much. And as a concrete example, in the figure on the right, here we had only 5 training examples and we fit a certain straight line, and when we had a ton more training data, we still ended up with roughly the same straight line. And so if a learning algorithm has high bias, just getting a lot more training data, that doesn't actually help you get a much lower cross-validation error or test set error. So knowing if your learning algorithm is suffering from high bias seems like a useful thing to know, because this can prevent you from wasting a lot of time collecting more training data where it might just not end up being helpful. Next, let's look at the setting of a learning algorithm that may have high variance. Let's first look at the training error. If you have a very small training set, like 5 training examples shown on the figure on the right, and if we're fitting, say, a very high order polynomial, I've written a 100th degree polynomial, which really no one uses, but just for illustration. And if we're using a fairly small value of lambda, maybe not 0, but a fairly small value of lambda, then we'll end up fitting this data very well, but with a function that overfits this. So if the training set size is small, our training error, that is JTrain of theta, will be small. And as this training set size increases a bit, we may still be overfitting this data a little bit, but it also becomes slightly harder to fit this data set perfectly. And so as the training set size increases, we'll find that JTrain increases, because it's just a little harder to fit the training set perfectly when we have more examples, but the training set error will still be pretty low. Now, how about the cross-validation error? Well, in the high variance setting, our hypothesis is overfitting, and so the cross-validation error will remain high even as we get, a moderate number of training examples. And so maybe the cross-validation error may look like that. And the indicative diagnostic that we have a high variance problem is the fact that there's this large gap between the training error and the cross-validation error. And looking at this figure, if we think about adding more training data, that is taking this figure and extrapolating to the right, we can kind of tell that, you know, the two curves, the blue curve and the magenta curve, are converging to each other. And so if we were to extrapolate this figure to the right, then it seems likely that the training error would keep on going up and the cross-validation error would keep on going down. And the thing we really care about is the cross-validation error, or the test set error, right? And so in this sort of figure, we can kind of tell that, you know, if we keep on adding training examples and extrapolate to the right, well, our cross-validation error will keep on coming down. And so in a high variance setting, getting more training data is indeed likely to help. And so this again seems like a useful thing to know if your learning algorithm is suffering from a high variance problem, because that tells you, for example, that it may be worth your while to see if you can go and get some more training data. Now, on the previous slide and this slide, I've drawn fairly clean, fairly idealized curves. If you plot these curves for an actual learning algorithm, sometimes you will actually see, you know, pretty much curves like what I've drawn here, although sometimes you see curves that are a little bit noisier, a little bit messier than this. But plotting learning curves like these can often help you figure out if your learning algorithm is suffering from bias or variance, or even a little bit of both. So when I'm trying to improve the performance of a learning algorithm, one thing that I'll almost always do is plot these learning curves. And usually this will give you a better sense of whether it's a bias or variance problem. And in the next video, we'll see how this can help suggest specific actions to take or to not take in order to try to improve the performance of your learning algorithm.